introduce Olivier Bousquet from Google, and a bit of background. So Olivier did his PhD at École Polytechnique in machine learning, and yes, I think it takes a moment. And if you can believe it, joined Google, I believe, 18 years ago?
Oh, yes.
Is that right? So he has seen machine learning at Google scale, evolve in many ways. And pre-LLM world, my understanding is you were doing a lot of work on new mathematics for understanding AI at the time. And now you're doing AI for understanding mathematics. So incredible. So thank you very much.
Thank you for the introduction, and thanks for the invitation. I must say that, coming from a machine learning background, this conference has been really enlightening for me. It's a pleasure to see the diversity of topics that have been covered, like from philosophy, education, foundations, Fermat's last theorem, and more. And I must say that the previous talk that we have seen, they have pretty much prepared the ground for my talk, where I'm trying to I will show you experiments that we've been conducting, and this is the work of many people, not just me, from Google DeepMind. And we've been trying to experiment what would it mean to use LLMs in formal mathematics in different ways. You've seen the talk of Thomas on AlphaProof on Monday, but this will be a complement to that talk where I'll describe experiments we conducted to do formalization and informalization using LLMs. And so the motivation really is that, as we have seen through the talks before, there are lots of advantages to formalizing mathematics. I don't need to convince you. I think you all are convinced of that. But the process is really tedious of formalizing, for good and bad reasons, but it's very tedious. And not only it is tedious, but even when the mathematics is formalized, it's not easy to interact with the result of that. I mean, of course, there are plenty of Lean experts that are perfectly fluent in Lean, but for us that are not, it's quite painful. And there have been attempts to make this more readable and having languages that are a little bit closer to natural language. And as we've heard, LLMs have shown some promise or have been experimented with in this space. But really, can we imagine to do formal mathematics in natural language without having to read or see or write Lean codes? Could we do Lean without Lean? That's really the question that I would like to ask, and I will try to show some little experiments in this direction. Maybe another way to characterize this is Terence Tao was mentioning this thing of doing post-rigorous mathematics, where you understand all the rigors of mathematics, all the details, but now you want to think at the level of ideas. You don't want to have to bother with all the details. And maybe LLMs, as we've seen in Alex's talk in this dialogue from Kim Gower's paper with the machine, you want the machine to take care of the details, but you want to interact very naturally and fluently with the machine. So I'll talk about LLMs a bit more in more details, even though we've seen some of that already before. And then I'll talk on about those two sides, auto-formalization and informalization. So let's start with LLMs. We all know, or I mean, you all know already quite a bit about LLMs, but let me go a little bit into details of how they work, and in particular, how do you make them to perform as well as possible? And there are three ingredients. One is what is called the pre-training. Then there is the fine-tuning or reinforcement learning. And then there is how you use them and how you interface them with tools. And all these aspects can determine the performance that you get at the end. So pre-training, Alex again had this nice metaphor of, you read a book and before turning the page, you try to predict what is the next word. And that's exactly what these models are trained for. So you take a bunch of, get used to this. So what you see here is the architecture of a transformer. So it's a big network with lots of weights that you can tune. And what you do is you collect a bunch of data from the internet, and you take arbitrary sentences, and then you put the beginning of the sentence as an input to your model, and you try to predict the next word. And whenever the next word is correctly predicted, it's all good. And if it's not correctly predicted, you tweak a little bit the weights until it correctly predicts all the words in the sentence. Okay, so that's pre-training. Supervised fine-tuning is another stage of learning that you do afterwards, where, because the pre-training really, like, you train your model to just continue sentences, really. And that's not very useful when what you really want is not that the model continues sentences, but that it answers questions. But answering question is really another form of continuing sentences, really, where, like, you have a sentence that looks like this: why is the sky blue? And then you collect some expected answer. Let's say you want the model to, like, you ask someone to write down an answer to this question, and the person would say, well, the sky is blue because blah, blah, blah. And now you want your model to be able to answer that question, and what you do is you, again, chop up this sentence into pieces, and you train the model to, whenever this question appears, predict the words in that answer. Okay, so it's similar to, like, it's the same process as the pre-training. The only difference is the way you collect the data is different. Instead of just grabbing everything on the internet, you create really pairs of questions and answers. And then there is the reinforcement learning variant, which is even easier to produce. Again, very similar training process. Now the difference is that instead of having questions and answers that you collected, then you have questions only, and a mechanical way of providing a score to any answer. So you don't know what is the right answer, but you have some way, some programmatic way, or some, I mean, you can also use humans, but, like, usually you try and do it programmatically, some way of judging whether the answer is correct or acceptable or good or whatever, and scoring it. And if you have that, if you can score the answer, then you let the model predict the words, and then at the end, you give it a score. If the score is high, then you train more on these kind of answers, and you encourage the model to produce more of these kind of answers. And otherwise, you try to kind of divert it from producing the answers that are bad. Okay? So, and if you look at, so, you know, these ingredients have been used and used over and over again to improve the models. And if you look at the timeline of how these models have evolved, it's quite fast. If you look at it, back in 2018, the models were barely able to produce sentences that look like proper English and that are somewhat on topic, about that remain on the same topic as what you're talking about, and really it looked like just a stochastic system that produces words that are statistically correct in the context, but not really much more than that. And over time, they have evolved to produce more and more interesting results and be able to actually solve problems, and harder and harder problems, interacting with tools, producing complex chains of reasoning, and it seems that some people have predicted, oh, but now we've used all the data on the internet, so what else can we do? Well, actually, we can still do a lot, and especially with these techniques of reinforcement learning, you can have the models generate their own data. I think you've all seen from the talk of Thomas this zero approach, where you try to set up the system such that it produces data and it learns from the data that it produces. And, like, if you can do that, and which I would argue it's mathematics is a domain where this is possible, at least for some tasks, there is in principle no real upper bound to what we can do with these models. Okay, and so now let me go a little bit into details. What we have observed over these years, more specifically about, like, what works and what doesn't work, are the following things. So one thing is that, of course, if you have more data, you produce better generations with your model. Another thing which is interesting is that, and that's the insight that is used in reinforcement learning, is that verification is often easier than generation, right? Like, it's easier to judge whether something is good or bad than producing something good in the first place. Using tools usually reduces hallucinations. Again, Alex demonstrated it with the, when he was asking, what was it, like 99 to the power 1,000, then Claude was using a Python piece of code instead of just trying to predict the next word kind of approach. Another thing is like if you have accurate reward, if you can judge precisely the quality of the answers, you get more value than trying to give example of the perfect answer, especially when there is no perfect answer, but there are like a range of possible valid answers. And finally, like the self-play ID is a good way to produce data and generate more data. So now, how do that apply to formal mathematics? So now let's go to the topic that we're interested in, and let's see whether these insights could be applied and in what way they could be applied. So, having more data helps generation. So that would lead to the fact that if you want to produce English, likely because the model has seen so much English, it will be better than producing Lean. So that's already a hint that going from Lean to English is probably easy. Going from English to Lean a bit harder because just the sheer amount of Lean data that the model has seen is lower. Another thing is because verification is easier than generation, then we can use this idea to, well, let's ask the model to verify as opposed to generate whenever we can. Using tools, well, we have Lean. It's a very powerful tool, and it gives you a very interesting signal. And that signal is very accurate. So, let's use it. And self-play, this is the idea, again, that is used in alpha proof of using search to generate more and more examples. So now let's see what we can do with that. And again, I won't repeat everything that Thomas has presented. So instead, I will focus on these other parts of the formalization pipeline, which is not proving, but really the input, the auto-formalization, and the output, like informalization, going back to English. And even more specifically, on the auto-formalization, I will only talk about definition and statement, not so much about proofs. And informalization, it will be the flip side. I will talk only about proofs. So now let's go into some of the details of this. So what we did is the following. Like it was like an idea to experiment with these models and see like how far we can push them to produce relevant formalization. So we focused on taking advanced mathematics as found in archive papers, like random archive paper, and see like whether we can extract a bunch of like definitions and theorems and formalize them. So we created this, what we call formalizable units by identifying claims, which could be lemma, theorems, or conjectures, extracting all the definitions from the paper, build some sort of graph of which definitions are used to formulate which claim, and then build some small set of these. Archive contains lots of them. Of course, we did not formalize all of them, but we took a subset and played with that. This is just a depiction of the process. So we, given the paper, we extract the LaTeX source, we extract all the definitions and the claims, then build some sort of a graph and say, oh, this claim depends on these definitions, and this definition depends on that definition. And then we take that small unit and try to formalize it. So let's see like the claim extraction first. And already there is some non-trivial behavior of the models. So this is just some random example. There is this paper, and in this paper you have this theorem. And like if you want to properly formulate that theorem, you need to define all these notions, like what is a Puise monoid, and what does it mean to be nearly Fürstenberg but not almost Fürstenberg. And well, it's all defined in the paper, but now you have to go fish for those things, right? So there is somewhere in the text, a Puise monoid is an additive submonoid of the positive rationals. Okay, good. Then nearly Fürstenberg, if there exists, blah, blah, blah. So there is a definition. Somewhere else you see almost Fürstenberg and nearly Fürstenberg. And you can see that almost Fürstenberg is defined at the level of elements of the monoid, but then the monoid itself is called almost Fürstenberg if every element is almost Fürstenberg. Okay, so like the way it's presented in the paper is not like a list of definitions. It's somewhere scattered around. But already with an LLM, you can say, well, find all the definitions that are needed to formulate that claim, and it will, fish them out and write them in like how you would write definitions one by one. And it pulls out also things that are needed, like, there was this notion of atomic element or atom, and so on and so forth. Now, actually, I freaked out when I looked at this example because I realized there was a bug. But the bug is in the numbering of the theorem. Actually, there is another theorem that's 3.7 that reads almost the same, but it's different. But fortunately, the theorem that is extracted is actually a theorem in the paper, just with a different number. But okay, you have to be careful. That's my point, is sometimes there are subtle errors. In this case, it's not a...
The error in definition 2 is not so subtle.
Yes, so indeed. So actually, this is another interesting point. Indeed, like somewhere in the paper, it says we will consider all monoids to be cancellative commutative monoids in this paper, which gets translated into a definition by the LLM, which fortunately is not then, it's skipped over when the formalization happens. So it's kind of, yeah, it's like, maybe it's not explicit, it's not really an error, because it really means, a monoid in that context means this, right? But yeah, I agree that's, yeah, good catch. Okay, now the next question is like, okay, imagine we formalize whatever I showed you. Can you evaluate automatically the result? Because of course you can look at it and it would take a lot of time, but if you want to get this process, this bootstrapping process started, you need some sort of automated evaluation. And so what we did is a combination of different things. One is like we check for errors automatically with Lean, right? Like if the Lean checks, then it's good. We check for sorries because often the code that is produced may contain sorries in the definitions. So of course they check, but it's not very useful. And then we use another LLM to judge the output. And in two ways. One is we ask the LLM, okay, does that formalized version correspond to the informal version? Like, does it match? Are there missing hypotheses? Are there missing details? Whatever. And also we do what is called cycle formalization, where we basically take the informal, formalize, and then deformalize, like produce again an English version of this. And we ask an LLM to compare the two informal versions, the one before and the one after. And that also is a good way to catch errors or missing, things that have been missed by the LLM. Okay, now if you just, input whatever I showed into an LLM and say, okay, please formalize. Unfortunately, it doesn't quite work out of the box. Sometimes it does, and Alex was showing examples yesterday. But one thing that surprised us initially is like it almost never gets the imports right. So imports, you can just forget it. It will cook up some random imports that don't exist. So in the end, we just put import matlib, and that kind of works. Definitions, they are rarely correct the first time. The types are okay, like the statement of the definition and the type is usually okay. The content of the definition is often much harder. Statements tend to be okay. Like it's easy to state a theorem if you have all the definitions, but if you have a theorems with lots of hypotheses, that's when it becomes a bit dodgy. Let's do an example. So that's the Prism monoid thing that I showed you before. So this is the first output of the LLM. Well, we replaced the imports by matlib, but that's what it produced in the first round. And there are some errors, like it uses addition, but this monoid is not defined as an additive monoid, so that doesn't work. It uses this weird thing of isUnit should be a predicate, but it says belong or not belongs to this, as if it were a set. Weird things like this. So if you just take random archive papers and run this, basically, roughly we get 1.5% of the attempts lead to something that checks in Lean. 1.1 are actually complete, like no sorries, and only 0.6 pass this other check of like asking the LLM whether it's correct or not. So it's fairly low.
But out of 400,000 papers, it gets 0.06%. That's a lot of papers that it got
Yes,
right.
yes. That's still like,
That's incredible.
yeah, that's still quite a lot. I mean, in terms of absolute number, it's non-trivial. Now, keep in mind that in archive, I'll show you stats later, but in archive, there are lots of very simple lemmas. So this is not paper-wise, it's lemma claim-wise. So 0.6% of the claims.
Of the 5 million claims.
Right,
Which
right.
is even more.
That's a lot of claims, but you know, there would be things like, yeah, there would be things like, you know, recall that addition is commutative, or I don't know. I mean, like, not all these claims are advanced mathematics claims. That's
Already if them advanced mathematics.
Sorry?
Already if them advanced mathematics.
Yes.
And still, you are not talking about proofs.
No, this is not proofs. Yeah. Also important. This is only definitions and claims. Okay, and there's also another caveat is that this is programmatic, so it's correct. Like, you know, when I say 1.1, it means 1.1. Whereas here, because it uses the judgment of an LLM, it's not entirely trustworthy. Roughly, it's, I would say, about 80%. By, you know, eyeballing a bunch of examples, it looks like whenever the LLM says it's good, well, it's only 80% good. Like, but it's rare that the opposite happens, that the LLM says, no, it's not correct when it is correct. So there are false positives, basically. Okay, so now let's see, like, how can we improve this 0.6%? Can we even improve it? So we tried different things, like using better models, using better prompting, and doing some fine-tuning. And yeah, like, you know, as we go down, it's more effective but more expensive to do. So better prompting, like, we use 3 different approaches. One is, okay, of course, using the lean feedback, like the errors that come back, and showing that to the LLM, asking to correct. Separating definitions and claim, it's easier to first formalize definition, do a bunch of passes, like to make sure they are correct, and then formalize the claim, and then use lookups in the library. That's another natural thing to do. So this is, yeah, now this box is filled in, like we formalize the definition, we do some iterations to fix the bugs using library lookups, and then we formalize the claim with the same technique. So let's see in action. So that's the example from before. So first thing the LLM does is it tries to fix this addition problem by, you know, changing the cancellative monoid to an additive cancellative monoid, and now addition works. That's fine. Now you still have this, you know, this membership issue here, which now gets, it makes an attempt to correct it. It says, oh, it's probably a proposition, so let's do, you know, let's use that as a proposition. But it turns out that in the monoid, in the additive monoid, then the unit is like just 0. So next round, it will correct it and say, well, okay, A not 0 is the same thing, so that's correct. So now all the definitions are, oops, correct. And then it tries to formalize the claim. That's the claim. It also has some errors. Actually, these are errors unrelated. Like I had a bug in when I copy pasted, but the real error is here that this is the fact that there is no isomorphism, and the correct way of doing it is to say not non-empty this set of isomorphisms. But eventually, like with enough rounds of correction, it does get something that checks. That's the point. So, well, okay, and so it's correct in the sense that it matches with the definitions. Notice that, you know, it doesn't, like, you know, this definition that you pointed out of whatever every monoid is a commutative cancellative monoid is not used as a definition anymore. It's just like in this context, M refers to an additive cancellative commutative monoid, right? So in that sense, it's correct, or it matches the original definition. Now, some stats, like as you do more and more steps, you can see that so blue is the whatever checks increases. kind of monotonically to a high percentage. So you can get something that checks in. Now, if you look at the thing is that as it does more steps, it tries to formalize and fix the errors, but it kind of gives up at some point and puts some sorries. Like, oh yeah, I can't formalize this, let me put a sorry to continue. So in a way, those that are actually without sorries, they don't climb as high. They only go to about 25% or something this. But you still get quite a bit, 25% now are possibly correct. But okay, again, with a caveat, because if you look at what is correct, again, judged by the LLM, it only goes up to about 2%. But the fact that we use more steps really helps go, more steps of feedback really helps go high. Okay, so that's first thing. Take a default model, do a bunch of passes of feedback, and then you get to about 2%. Now let's try something else. Let's try to allow the model to look up definitions or declarations in MATLAB or doc strings in MATLAB. So if we do that, so that's the baseline, like without any lookup. If we do a lookup where we say, oh, tell us which names you would want to look up in MATLAB, and we do an exact match on the name, you get a little bit higher. And if you do some approximate match, because sometimes it would be, oh, I need to look up the signature of that function. I know the function, I just need to look up the signature. But very often it doesn't know the name correctly of the function that it wants to use. So if you do approximate match, you get a bit higher. Okay, now another thing we can do is change the model, because there are different generations of model. So this is the one from before, 1.93%. If we use the previous generation, that was Gemini 2.5 Flash, if we use the previous generation, it's 1.6. So indeed, as we go up generations, like without doing anything related to mathematics or to Lean, it improves. And another thing that was surprising is if you take a bigger model, like instead of Flash, you take Pro, it's almost double. So you could say, well, maybe we should just sit back and relax. Let's wait for the models to get better, and they will be better at mathematics and formalization anyway, without us doing anything. But yeah, that's plausible, but we can still explore different things. And so that's why we also did some fine-tuning to see how we can improve, again, from this baseline of 2.5 Flash. If we take some of the successful examples that are correctly formalized, and then we retrain on them, as we get more and more examples, we also improve the performance. Unfortunately, even though the curve looks promising, it kind of plateaus after. There are various issues, like the model starts to try and break down the Lean code into different pieces, because it starts to insert steps of reasoning within the Lean code, and it's a bit harder than to kind of reassemble the Lean code afterwards. So there may be ways to fix that, but we haven't got to doing it yet. So this is a good example where things worked pretty well. The initial thing here, you see that, maybe I go back. Here we have, so the definition of a map that has a certain property, and here it just says if phi is self-adjoint, then blah. Without saying that phi in that claim has to be a map of this type. Of course, it's implicit in the context, it's implicit in the fact that this is using that definition and so on. But then it's corrected in the formal statement. So my point is, sometimes there are mistakes in the extraction of the claim, but they tend to be corrected because in the end you want something that checks. Another issue here is that there is a notion of a star ring in MATLAB, and it doesn't use it. It uses the fact that there is a ring and a star, and it kind of reinvents the definition of a star ring. So it doesn't know MATLAB that well, basically, but still. Okay, now another aspect to it is that you could say, well, but this is all definitions. What about proofs? And surprisingly, some definitions involve proofs. And again, the model is able to create proofs. So this is an example where you have to define what is a minor in a hypergraph. So a hypergraph is like a graph, but the edges, instead of being pairs of vertices, they are like arbitrary subset of vertices. And I don't know if this is the the most elegant way of formalizing a hypergraph, but that's what it the LLM proposed. You have a set of vertices and the set of edges. Each of these edges is a set of vertices, and then you have some proof that the edge set is a subset of the power set of the vertices, right? So that's how it was formalized, and then you now have to define what is a minor. A minor is like if you have a hypergraph, an hypergraph minor is another hypergraph that you obtain from the original hypergraph by deletions and contractions of edges. So now you have to formalize what does it mean to delete a vertex in a hypergraph. And again, this is all generated by the LLM. So a vertex, when you have a deletion, you get a hypergraph which has the same vertex set except for that vertex that you deleted, and the edges are all the edges that don't contain that vertex. And now you have to prove that this property is still preserved as you do this deletion. And it kind of cooks up a proof. I mean, I don't know whether it's the most elegant or the most natural, but it cooks up a proof. Then it does the same thing for contraction, and then it expresses that being a minor is if you can go from one to the other by a sequence, like it's using an inductive definition of deletion and contraction. So it's kind of nice, except that it's wrong. At least, okay, the deletion is correct, the contraction is incorrect because contraction normally refers to contracting an edge or hyperedge instead of a vertex. And here it defines some weird thing of removing a vertex and then replacing the edges by removing all the edges, removing this vertex from all the edges that contain it, which is not correct. But the point here, I mean, and another interesting thing is that this passed the check. Like the LLM said, oh, it's all correct. It all matches with the original definition. It's all good. So
it's not correct. You mean that this was not the actual definition in the paper.
Yes. So this is just a reminder that these things are all great, but sometimes there are some glaring errors of this kind, which still mean we have to check. But
how is it coming up with these proofs?
So it knows it has to write the definition, and because the hypergraph is defined like this, it knows that here you have to write a proof that this holds, right?
But that's probably not in the paper because the paper just assumes you know.
Yes, yeah, that's correct. Yeah. So this proof is not at all in the paper because the paper would just say, oh, you have to do deletions and contraction. Actually, I did not check, but I'm assuming the paper would not even define what is a deletion and a contraction because it's such a well-known concept in that domain. So it has to struggle to figure out what actually is meant, and that's why it makes mistakes also because it's not provided in context.
So is the proof written in one shot, or is this one of the things that it gets
that takes a few iterations. Yeah, the proof is like there are some little bugs here and there, but with the feedback it can correct that.
Is it like alpha proof that's running on this, or
No, this is pure Gemini. Yeah, and it's a kind of orthogonal approach to alpha proof, where alpha proof would go line by line, whereas here it produces a whole thing, gets the error, rewrites the whole thing, gets the error, and so on. All right, and then I was mentioning these statistics. So, sorry.
Does the system only knows the previous error, or all the previous errors at each time?
So in the current setup, what we do is we only show the latest version of the code and the errors, not everything that has been done before. So it may sometimes loop and say, oh, try to fix the error and then fix again. But it's kind of more efficient because if you accumulate a long context, it takes forever to run. So just a trade-off. Here's some statistics. So these are like the breakdown of categories in MATLib, in Archive, sorry. And like the fraction of papers that are in each category. So it's sorted by the most frequent and to least frequent. And here you see the success rate of, it was some version, like doesn't matter, the absolute numbers don't matter. What matters is the relative numbers, like how successful are we at formalizing statements from these papers. And you see that the easiest one is history and overview, not surprisingly. Like usually it's like, oh, Pythagoras theorem is like this, like that. Or general mathematics, which tends to be fairly low level, I would say. Or, well, general topology is not bad as well. K-theory and homology, 0. So that's kind of out of reach currently, given the state of LLMs and MATLib, maybe.
But the IMO performance did poorly, most poorly on combinatorics, right?
True, even though like it's not so bad, not so hard to formalize. And again, remember this is all definitions and statements, not the proofs, right? So formalizing definitions in combinatorics is not too hard because usually they don't involve complex notions. Solving the problem is another story. Yeah, another thing that we were surprised is like also differential equations, not too bad. PDAs, we were expecting a much worse performance, but yeah.
You're relying on this LLM's opinion.
Yes. Again, with the caveat that this is only at best 80% correct, these numbers.
Yeah, and you didn't look at mathematics that lives in archive physics, because there are lots of mathematics.
True. Yeah, we only looked at archive mathematics. Yes. All right. So with that, yeah, just to conclude that section and moving to the next section. So again, right, we're not trying in this experiment, we did not try to get, MATLib grade definitions. Right? We were happy if the definition checks and is sufficient to express the claim correctly. So, maybe it's not very elegant, maybe it's not very general. As long as it is correct, we are happy. But as we observed, there are still lots of issues. The training, like, doing the fine-tuning did not quite work as we were hoping, so we are still working on that. MATLib search would be helpful, like to do a more powerful search, because very often it tries some guess of what would be the right definition, doesn't work, try another guess, and then keeps trying, and never succeeds. It's also like, yeah, there is this issue that there are certain notions that are very standard in normal mathematics, but that are not quite formalized as easily in MATLib, like the notion of a vector space. Well, you have to use a module with a field. That always, trips up the LLM. Also things like, partially defined function. Like if you do define a limit, which usually takes a real value, except when it's not defined and it's infinite. And that's what we've seen in Flory's talk, like he's using like these extended reals. That's, tricky for the LLM to get right. And again, human oversight is still necessary if we want to be faithful to the original. But I think, we still, we were surprised to see that it's still producing something very decent in a large number of cases. Now let's see how we go back the other way. And one motivation is that one thing that kind of worries us is that as we get more and more mathematics formalized, as we get these theorem provers more and more powerful, and someone said on the first day that we can just be watching the machines come up with proofs and sip margaritas when they do the work. I think, yeah, that's not the future that we want to be in, right? We don't want to be like, watching the robot write proofs and like, us trying to ask questions and not understanding the answers. We want like to work collaboratively with the robot, ideally. So to do that, that means we have to kind of have some way of interacting in the other direction. Like the robot would, like alpha proof would produce like a gigantic unreadable proof, but we want to understand like what are the insights, what is interesting about this proof, like what is the key idea and stuff like that. And so that motivates the informalization, but there are like many different things you can be doing when we talk about informalization. You can just explain some link code, that would be already useful, or provide a full natural language proof from either a proof that someone has written, that's already useful, or a proof that a machine has written. Or maybe, even simplifying proofs, as we saw in Terry Tao's talk. Sometimes it's useful to go back and forth between formal and informal so that you kind of refine the proof. And there are different formats in which you could want this informalization to be, like comments in the link code, or some big file that explains the proof, or even some interactive UI. And I will repeat what I said before. I think a lot of this came from inspiration from the work of Patrick Massot and Kyle Miller, this this demo that they showed that you know, going from a lean piece of code to some interactive UI where you can click and zoom in and zoom out. So we wanted to see whether this can be done not programmatically but with an LLM. And of course, lots of caveats apply because we lose a lot when we go to an LLM, as we've seen. And I guess it's a bit of a, you know, trade-off curve here, where the good thing about the LLM is that it always spits out something. But you know, a more positive way to say it is that, like, you know, no matter how complex and the construct is that you're using, it tries to make sense of it. Which is unlike the programmatic approach, where if you did not anticipate in your set of rules that, okay, if there is this tactic being used, then you should write it in natural language in that way, well, you get nothing, right? So you have this trade-off between how many different cases you can cover versus how correctly you cover these cases. So yeah, we thought it's worth exploring this other corner of the space. Okay, and you know, again, first surprise is that sometimes it just works. So there is this theorem, and well, you just ask, it produces a complete and clean, you know, explanation of what the proof is doing, spelling out the equations. Like, you know, for example, it uses the formula for addition of tangent, and now it, like, the LLM would spit out this formula, even though it's not in the original code, but it knows it somehow. So that, you could say, is a very useful way of rephrasing that proof here. Yes.
How much of that is prior knowledge of Gemini from reading calculus books and screen training?
Yes, it's actually it's exclusively prior knowledge, because indeed the input to this, in this case, is exactly just this. So, you know, if you see, as a human, if you've never seen any lean code and you see tomod, tan add, you know, what do you know, right? But so, in a way, it's like a combination of pre-training from mathbook, also having seen some lean code, and doing some guesswork. And, you know, sometimes it would not even look at the proof itself, just look at the statement and try to come up with the proof.
Because case 2 is completely unrelated. What is written in the case 2 is unrelated to the lean.
So lean doesn't.
I guess it comes, or maybe it has the cases in the wrong way.
I mean, the lean code has some content.
No, because it, like, you know, by cases, like.
Right, and then there are these two dots, and the first dot is when H is true, and the second dot is when H is false.
Right, right. So it's. Isn't that corresponding to those two?
The LLM output for case 2 is this case doesn't need to be talked about because it says infinity, because neither side is defined.
Ah, yes, you're right. Yes.
And you have to do something, and lean does it. And it's just completely.
Oh yeah, no. This, you're right. This is actually in this case it's junk. Yeah, I agree.
But the LLM is correct.
Yes.
It's
so and that's indeed you see that a lot. I'll give you more examples. Yeah. So, but okay. I guess the point I want to illustrate here is that it tries its best by reading this and trying to infer what possibly is going on, and that's not always sufficient. Sorry?
Natural language division is different from lean division.
Yes, that's another, yeah, indeed, case where things go.
It's written what's correct for the natural language division.
Yeah, because it's in the pre-training.
Yes. No. So yeah, the problem with this approach is that it tends not to be faithful to the lean. So how do we fix that? Or okay, maybe another example. Okay, in this case, it's you know, we went and, like, because before it was just, you know, taking the proof, the theorem and the proof, and trying to informalize. And here we said, okay, why don't we can just go entire files? Like, we take a file in MATLib, and we say, well, write a LaTeX document corresponding to it. And, you know, sometimes it does something fairly reasonable. I mean, of course, this file is not too complicated. There are not complex proofs. But, you know, it does something that is very readable and largely correct. But, okay, of course, we want to go further. And our target really is to try and make sense of proofs like this. This is a proof by alpha proof of this theorem here. And well, I mean, to me, it's largely unreadable. There are lots of cases. You know, it breaks down into lots of cases, and it uses a lot of, you know, this omega tactic. So it's, yeah, like I would want to see like a simple, succinct proof, or at least understand what's going on here. And
Do you know the source of this question?
the source?
Yeah, is this question just, was it on some IMO or something?
This one, it's either IMO or maybe some forum.
So it's on the internet.
Yeah, it's somewhere on the internet, yeah.
So you presumably have the problem that this is not actually the ideal proof of the statement. Like alpha proof is come up with something, but it's not actually how the statement should be proved.
It's not very helpful, let's say. It's,
right, but I mean, maybe you should clean up the lean code before you translate the lean code to English.
yes, no, you're right. The lean code itself is not, like, yeah, there are two aspects to it indeed. The lean code is probably not the best possible proof for this statement. Maybe there is a more direct and more elegant way to do it. But assume that that's all we have, and or like, you know, I'm thinking in the future, like at some point we'll get something like this for new theorems maybe that we haven't proved ourselves or that we don't know how to prove ourselves, and then we'll say, oh, what do we do with that, right? So it's kind of a good use case to try and see whether we can make sense of something like this. Of course, this particular example probably is junk anyway, or I mean, it's a correct proof, but mostly junk.
But I think it's an interesting question.
But, yeah.
If you've got a future alpha proof that is producing objectively terrible proofs of the statements, do
Right.
you want to try to explain to people how the objectively terrible proof works, or do you want to
Yes, or to improve, yeah, yeah. I think realistically we want alpha proof to produce proofs that are more understandable, but we're not there yet. And just, you know, to give you a sense of, like, because of course we compared MATLib proofs and alpha proof proofs, and like if you take random proofs in MATLib, they have on average like 2 lines, because everything is so modular, so, you know, broken down into simple lemmas, and like, you know, there are APIs and whatnot. So it's really like very small. There are very rarely proofs that exceed like, I don't know, 10 lines. Whereas alpha proof, like in the early versions of alpha proof, it was like already an average 7 line. And now, like, I think the current version is, you know, and of course the proofs on which we, or the theorems on which we try to run alpha proof are getting harder and harder because we want to train it. But it's not unusual to produce, you know, proofs with like close to 100 lines. So the average is 33. Right?
You say average line, you keep saying average lines, but on the screen it says average tactic.
Oh, yes, sorry. Yes, my bad. So indeed, it's like measured in tactics. Like these numbers are really tactics, but it's just like roughly 1 line equals 1 tactic. It's not true all the time, especially like, you know, if you have nested tactics, like if you do a half statement.
The average number of distinct tactics.
Well, okay. Tactic means in this case, okay, actually it's the wrong name. It's a syntactic unit where you know, when you parse it, you have a state before and a state after. So it's, yeah.
You're allowed to use a tactic more than once.
Yes. Exactly. Sorry. Yeah, but think of it as more or less lines of code. Now, yeah, like to your point, Heather, on what kind of junk alpha proof produces. These are some examples which you find in the proofs. So, like, you have this statement where it keeps repeating, you know, square root of 4 equals 2, square root of 4 equals 2. Okay, sure. If it's true once, it's probably true many times. Or it has like this very obscure or convoluted way of nesting things, like it says exact, by and linear it, and then by norm. Like unpacking all that is really tricky. And unfortunately, like if you just see this line and you see the states before and the state after, really hard to make sense of what's going on there. Another thing, like, you know, it would, and I think Thomas mentioned that, like, showed some example, like it would introduce some random irrelevant hypothesis, like the fact that 5 factorial plus 0 equals 5 factorial. Not very useful. Or it would, you know, use unnecessary parentheses.
Well, maybe it's a very naive question, but I was looking in the convoluted nested practice. There is no space between comma and pause. So all commas in MATLAB
yes,
come with a space after. So how did it come with some type of encode that doesn't
Ah, yes. Okay, because it's not trained only on MATLAB. It trains.
So there is so much.
Rubbish.
Yeah. No, it trains on what it produces. So it kind of invents its own language over time. Because if it sees that this checks, well, it keeps doing it. Because why wasting time on putting a space, right? Although, you could argue it's kind of weird. But it's so that, adding parentheses is kind of a good thing. So it kind of keeps adding them.
Because when you're doing reinforcement learning, you're generating tons more mathematics as there is in
Yes. Right. Yeah.
So I mean, are these sort of syntactic junk tokens for chain of thought to like?
No, because alpha proof is really just spitting out lean code, not.
No, it doesn't have a.
Yeah, it doesn't have a chain of thought, at least at this point. Okay. So let me briefly say what we tried to do to improve that situation, not on the improving what alpha proof produced, but on the side of improving what we can make sense of what alpha proof produced. And so, yeah, I have a few slides. Maybe I'll skip those because probably everyone knows what is a lean proof, and it was mentioned before that a proof is really a term having an expected type. But yeah, essentially, a theorem is just a function that takes a bunch of terms and spits out a term. And there are two ways to write a proof. One is directly, you construct that term, or you use tactics. And tactics are usually closer to natural proof, or the way we think about it. You break down you apply induction because you want to break down the goal into two separate goals and stuff like that. But tactics have very different levels of granularity. This is one example of the term that is produced by applying n-linearity to that inequality here. And notice I put a 2 because it's true with 1, but somehow n-linearity cannot prove it with 1. It proves it with 2. But anyway, and this is not all. There are 6 pages like this. So making sense of that is really hard. And you wish there would be some way of converting that into a simple proof. Yeah. Sorry?
Or just factoring, if you had even with the 1, just factoring.
Yeah, exactly. You would want it to say, well, let's factor this. And actually, alpha proof is kind of abusing those powerful tactics because, if it notice that when you put hint, it helps. So it puts hints everywhere. And, you can't really make sense of whatever. And so, yeah, now I think Alex showed that very nicely, that this notion of a game board, right? That's, there is the proof, but there is also what happens at every step of the proof, the state in which we are, you now have to prove this, and then now you have to break down this goal into 2 goals, and so on and so forth. And unlike the game of chess, where it's mostly linear, in this case it's actually more of a tree. The game board is structured as a tree, and so you can basically create a tree that represents the structure of the proof, where each node in the tree is the state at which you are, what you have to prove next, and then you break down into pieces. There are subtleties, there are meta variables that introduce connection between the goals, so it's not quite a tree, but almost. And it's maybe. So yeah, let me just say what we do. We take that tree, we extract the tree from lean, and we try to informalize every step of the tree, showing what was the state before, what is the tactic we applied, what is the state after, and this usually makes sense. And then we try to aggregate that into a coherent proof. And maybe I'll just show you the result, which is kind of aspirational at this point. So this is the kind of tool we would like to build. It kind of works, but is not ready from prime time. You have a proof that you upload in lean, and it automatically informalizes the step using the content of these goals, and you get a corresponding informal version of that proof, which is where you have a one-to-one mapping between the lean code and the proof. So you can see the interleaved version. Right, you can see for the statements in lean and the corresponding natural language version of it. And then you see this tree here that you can zoom on. Like you can visualize this whole thing as a tree, and yeah, and then like okay, we can also automatically generate some sort of summary of that proof again using an LLM. And the idea would be that you could edit that that content either by changing the lean code or by changing the natural language code. And if you change natural language, you can reformalize, and if you change the lean, then you can re-deformalize. And so iteratively, you have this object that you can interact with that is based on something formal, so there is correctness, but it's also like very natural to interact with because it's also show you in natural language. So, and with that, I will get to my conclusion, which is here. So basically, we have seen that LLMs are becoming really helpful. I mean, not perfect, far from that, I should say. Full automation is still far away. But if you couple this with alpha proof, of course, if you interleave like auto-formalization, deformalization, and proving, you have something that possibly can improve the workflow quite a bit. And so maybe we're one more step towards Tim Gower's golden age, hopefully.
Olivier. So before lunch, I think we just have time for a handful of questions. But
so I was wondering during the talk that maybe you can comment on this. What do you think on basically the? Do you think that there will be an existential crisis for formalizers as it happened, like, I don't know, 4 years ago with calculators? Like the classical, so do you think that there is an existential crisis with the formalizers, the current human formalizers, as
human
it is like,
okay.
given that the speed that, for example, I don't know, 8 years ago, if this talk would happen for, I don't know, language translators, when GPT-1 was at its very infancy, like people were, I think, were exactly seeing the same errors, basically having the same reaction. Should us as formalizers, I mean, not me, I mean, formalizers, I'm not like here, like in general, would feel the same existential, basically, feeling as basically 8 years ago with natural language?
Well, I would say let's ask Kevin, because Kevin is happy to delegate the work of formalizing to a community. Maybe he would be happy that this community includes some LLMs.
Yeah, if they can start helping, that's great.
Yeah, if it doesn't add burden, which maybe we're not quite sure yet, but yeah.
There's been extraordinary progress. You're just showing something. You're showing the beginning.
Yeah, pointing in the direction, hopefully. Yeah.
More questions?
And what's the problem with PD? Why it's so difficult to formalize?
PDEs.
Yeah.
Okay, to be honest, I did not dig into some of these results. I think part of it is the content in MATLAB, whether it's rich enough to express those things. The other thing is the knowledge of LLMs of that area of MATLAB, because even though it's there in MATLAB, the LLM may not know about it or may not be able to use it proficiently. But apart from that, and the fact that maybe like if you need too many definitions, then of course this process will tend to there was this idea that if you make many mistakes at every step, then it's hard to correct course, even though you have some strong guidance from the lean errors. So yeah, combination of these factors. Yes.
To what extent is good informalization a bottleneck for your auto-formalization? So if I could snap my fingers and Carl and Patrick had a year off and time to finish their informalization project, would that help your auto-formalization project?
Partially, yeah, I guess so. Because as you've seen in the auto-formalization, we use this cycle formalization, like we deformalize automatically. But in the auto-formalization, the informalization is just used at the very last step to check correctness. It's not perfect as it is. If it were perfect, we could rely a bit more on it, but I don't think it would change the game significantly. But it would change the game for all of us reading lean code and alpha proofs for sure.
So if you go, I mean, further into research mathematics, then you'll need to deal with the invisible mathematics that Emily, introduced, but it's not in the books because it's invisible.
Yes.
So how are you going to do that?
Yes. So and actually we did bump into this quite a lot. I think like everyone who presented formalization project implicitly showed that there are like all these subtleties that are not quite mathematics. I mean, sometimes it's mathematics, but sometimes it's also like just intricacies of using lean to formalize things. I guess what we've seen is that LLMs are not too bad at filling in some gaps, right? Both in proofs and sometimes wrongly, but also in definitions. Like sometimes they say, oh, well, there is this missing step here. Let me add it. And I guess so. Like for the mathematical aspect of it, we can hope that they can do some of it. But of course, that's where the human input would be useful. For the lean part of it, I think the self-training, at least what we've seen in AlphaProof, is that it seems to kind of to work on picking up. AlphaProof is able to pick up very advanced lean concepts without being told in a way, just by trial and error. So I think there is also some case to be made that eventually, it will learn how to use MATLib better and how to fit in the details, like the ugly details that you need to fit in to be correct and so on.
So you're saying we're learning the invisible mathematics because it's present in the lean code, not in the formalization.
Or because it will be necessary for the lean code to check. It will discover it possibly. I don't know if you still have time.
Go for the last question before lunch.
This is more of a continuation of questions by Filippo. So you just said it's not trained on MATLib codes or codes like actually written down by humans. I was wondering what was the kind of proportion you use? Is it 100% self-generated code or?
Oh, so the auto-formalization, we start from a Gemini model that has been trained on whatever is on the web, let's say. And then when we do the fine-tuning, we do the fine-tuning only on formalization that it has produced itself.
So if we finish some of the big projects mentioned in Big Two, such as FLT, it won't actually help.
No. I mean, at least in the current stages, in the current thing that I presented, not. Indeed, that's a direction of also possible improvement, is to train from aligned pairs. I mean, in a way, in this particular experiment, we did not use any aligned pairs of informal formal for the training, but that's certainly a possible direction.
Right. Thank you, Olivier.